Okay, we're going to start talking about kinetics, and we're going to come back to this a lot more later on in the year. So this is just kind of an introduction to it. Um, Most of nuclear chem doesn't depend on anything that is talked about before, but this is actually chapter 21 in the book, and this is the one concept that they sort of assume you have an understanding of before they go into it. So if you read your book, it's going to be a little bit confusing. I'm going to try and give you the background information that you need in order to understand this. But basically, kinetics, when we're talking about kinetics, you might think about kinetic energy maybe. Kinetic energy is the energy of movement. Okay, when we talk about kinetics, we're talking about the rate that something goes. Okay, the rate of a chemical reaction. So, how fast it goes, how slow it goes, that sort of thing. Okay, so radioactive decay. The reason we're talking about kinetics with that is that there are a lot of different radioactive isotopes that decay at different rates. So, some radioactive isotopes last for a few seconds, and then they decay into something else. Some last for millions of years before they actually decay into something else. So it just depends on what you're talking about, and we need to have some way to define the rate of these reactions. Okay, so nuclear transmutation, what we're talking about there is radioactive decay. In other words, a nucleus, radioactive nucleus, changing into a different element, the nucleus of a different element. Okay, this is a first order process, and this will make more sense once we talk about kinetics, but there are several orders that a reaction can have, and that basically just, that order describes how the concentration affects the rate. Okay, so you can have a zero order reaction where the concentration doesn't affect the rate at all. First order reaction where if the concentration doubles, the rate doubles, and that sort of thing. Then second order, concentration doubles, the rate quadruples, and so on and so forth. So nuclear transmutation is a first order process. Okay, now on your equation sheet, which you're going to get today in class, you should have gotten it in class. This equation is on there underneath the kinetics section, okay? And this is going to tell you how to calculate half-lives of nuclear equations. Now, they don't give you the actual half-life equation, but we can figure it out, okay? So the way that you do this, you have to know what each of these things means. This A right here in brackets, that stands for concentration of A. And in these reactions, concentration can be measured in a lot of different ways. So we'll get to some examples of that. But concentration of A at time t, okay? And that's kind of like your final time, or your time at the end, okay? And then this is concentration of A at time 0, or initial time. So this second part of the equation, the natural log of A0, is the concentration at the beginning, and then this other part is the concentration at the end. Okay, since we're talking about nuclear decay, typically the concentration at the beginning is going to be higher than the concentration at the end. And then K is just a rate constant, just a constant value. And we can calculate that K for each different type of nuclear decay. So for every type of nuclear decay, the K is going to be a little bit different. And then T is just time. Okay? All right. Hopefully that makes sense. I'll show you how to use this equation in just a minute. So kinetics is such a process, obey this equation. Now, half-life. The half-life for nuclear decay, if you want to calculate the half-life, here's the equation you're going to use. Okay, now half-life, we should talk about that for a second. Half-life is the amount of time it takes for 1/2 of the nuclei in a radioactive sample to decay. Alright, so if we start out with 10 grams of uranium, the half-life is how long it takes before that 10 grams, half of it has decayed, and now we only have 5 grams left. Okay, 10 grams of uranium going to 5 grams of uranium. Now the rest of that has decayed into something else, and now we just have 5 grams of the uranium left. Okay, so that's half-life. Now, you can actually get this equation from the equation on the page before. Weird. Okay, let me show you how here. Just 1 second, the fire alarm just went off. I'm going to pause this for a second, and then we'll maybe I'm going to pause it for a second. Come back to it. Okay, sorry about that. That's odd. So anyway, we were talking about kinetics, and we were talking about the half-life equation. Okay, now you're going to have to remember something here about natural logs, or learn something, depending on whether you've learned this in your math class or not. When you have logarithms and you subtract them from one another, so for example, like the ln AT minus ln A0 here, you can actually rewrite that as the natural log of AT over A0. You can kind of put them both in the same expression there. Okay? And so if we rewrite that in that way, AT over A0, and then we think about it for a second here, remember, half-life is how long it takes to end up with half the concentration that we started with, okay? So A0, let's say that starts out as 10 grams, and then AT, at time t, we end up with 5 grams, okay? So 5 divided by 10, that's going to give us the natural log of 1/2. Regardless of what the concentrations are, AT for the half-life is always going to be half of what A0 is. So natural log of 1/2 equals negative KT. Well, natural log of 1/2 ends up being, if you actually calculate out that number, 0.693. Okay, so then we've got the 0.693, or actually it's a negative 0.693, is equal to negative KT. And then if we rearrange that equation, divide both sides by negative K, then we end up with this equation right here. T1/2, which just means time of the half-life, equals 0.693 divided by K. The negatives cancel out here. Okay, and so this equation right here is not on your equation sheet, but it can be derived from the other equation if you remember just that little trick on natural log, that if you divide, or if you have a subtraction, a natural log subtraction, this works for logarithms too, just log of AT, this would also work. And we take the natural log of the one term divided by the other term, okay? And so when we get to half-life, one important thing to realize there, notice the concentrations have gone away, okay? So it doesn't matter what concentration you're starting with, the half-life equation is always the same. The only thing that the half-life equation depends on is K, your rate constant. In other words, how fast does this thing decay? So if you have uranium, for example, and the half-life is, a billion years, then once it's gone from 10 grams down to 5 grams, which it would take a billion years for it to do that, it takes another billion years for it to go from 5 grams down to 2.5 grams. The starting concentration doesn't make a difference. This is 1 billion. This is 1 billion. Okay, and then to go down to 1.25 grams, it takes another billion years. All right, so the concentration doesn't affect the half-life. The only thing that affects it is that K. All right. If we compare the amount of a radioactive nuclide present at a given point in time with the amount that's normally present, and a lot of times we can find the age of an object, which a lot of dating of old samples is done this way. Okay. All right. So here's an example. Half-life of cobalt-60 is 5.3 years. We want to know how much of a 1,000 milligram sample of cobalt-60 is left after a 15.9 year period. Now, you could solve this using the equation that we just talked about, okay? Or you can just sort of think about this. And some of these half-life problems are not that bad. In fact, I would say the bulk of them that you see on the AP exam are fairly easy to solve, okay? So the half-life is 5.3 years, right? So if we think about 15.9 years, the numbers work out pretty nice here. 5.3 times 3 gives us 15.9, right? So we're talking about 3 half-lives. Okay? So if we have 3 half-lives here that are happening, then we just need to think about what's going on here. We've got 1.000 milligrams of a sample, okay? In the first half-life, half-life number 1, this is going to decay down to half that amount. So now we've got 0.500 milligrams, okay? After the second half-life, the amount is cut in half again. So now we've got 0.250 milligrams, okay? And then after the third half-life, we've got 0.125 milligrams, okay? So the amount we're going to have left after 3 half-lives, which is 15.9 years, is 0.125 milligrams, okay? And again, I would say the majority of the nuclear radioactive decay questions you get on the AP exam are going to be that easy to solve, okay? Now, I want to prepare you in case they throw a more difficult type of problem at you, okay? And here's the more difficult type of problem, but this isn't that bad. It's just plugging into those equations that I just gave you, okay? So a wooden object from an archaeological site is subjected to radiocarbon dating. The activity of the sample is measured to be 11.6 disintegrations per second, okay? This is not a unit that you are familiar with, but disintegrations per second, that's just a measure of concentration, okay? So it will go into our equation that we talked about before. The activity of a carbon sample of equal mass from fresh wood is 15.2 disintegrations per second. So in other words, if you have fresh carbon, there's going to be 15.2 disintegrations per second, okay? We have a sample here. The disintegrations are 11.6 disintegrations per second, so this is not fresh carbon, okay? So we want to figure out how old it is, okay? In other words, what they're asking us for in this equation they're asking us for the T, okay? The amount of time this thing has decayed in order to become a sample that has 11.6 disintegrations per second, okay? So we need to plug into this equation, but the problem here is we have 2 unknowns at this point. We don't know the T, or the time, that's what they're asking us for, and we don't know the K. We don't know the rate, or the decay constant here, okay? We don't know how fast this thing is decaying. But they do give us the half-life. So remember, we've got another equation here. 0.693 over K equals T to the 1/2. And once we find this K here, we can plug it back into this equation, and then we should be able to find our T. All right? So 2 steps here that we're going to do. So 0.693 over K equals the half-life, which, I can't remember what they said, 5,715 years is our half-life, okay? So 5715. All right, so then once we solve for K here, and be careful, you need to multiply both sides by K, and then you're going to have to divide both sides by 5715. So this is going to be a small number. It is a lot of times with the K constant. All right, so our K here equals 1.21 times 10 to the negative fourth. And the units on this, because 5,715 is years, this is going to be years to the negative 1. Okay? Not a huge deal at this point, but you do want to make sure that you get your units right when you do this. Okay, so now we can determine the t in the other equation. So now we've got the natural log. Let me make sure I get the equation right. Sometimes I get this thing switched around. Natural log of a times t minus the natural log of a times 0 equals negative kt. Okay. Excuse me. So now we've got the natural log of a at time t, and that's going to be our concentration at time t. Sorry, I'm going to have to go back to that because I don't remember it. And again, time t is after it has decayed for a while. So this is our concentration at time t, 11.6 disintegrations per second. Minus the natural log of the concentration at time 0, which, coming back over here, is 15.2. That's our initial concentration. And that's equal to negative, and our K here is 1.21 times 10 to the negative fourth years to the negative 1, and that's times our T. Okay? So now we should be able to just calculate this and solve. When we take the natural log, and hopefully you guys know where your natural log button is on your calculator, it's just the LN button. Natural log of 11.6 minus the natural log of 15.2 should give you a negative 0.270 or so, and that's equal to negative 1.21 times 10 to the negative fourth years to the negative 1 times t. So if we divide both sides by this k, that should give us our time, and that would tell us the age of the sample in years, okay, because this is years to the negative 1 right here. So we divide that by and that gives us about, let's watch our sig figs here. I think we've got 3 on everything, so 2,230 years is the approximate age of our sample. So that gives you an idea of how they can date these things sometimes based on the amount of carbon-14 that's left in them. That's actually a process called carbon dating. And scientists use that a lot to date things that are, not incredibly old. A lot of historical artifacts can be dated that way because the decay constant for carbon-14 is so consistent. It's known exactly how long it takes for half of that carbon-14 in a sample to decay. All right. Measuring radioactivity, we can use a Geiger counter to measure the amount of activity present. And we talked about this last year, so I don't need to talk a whole lot about it now. I might pull these out tomorrow if we have time, just so you can be reminded of what they look like and how they work. But basically what's going on there is you've got a tube filled with a vacuum, or a tube that filled with nothing, it's a vacuum. And basically you've got ionizing radiation that's allowed to pass into it, Okay, so as an alpha particle or something passes into this opening right here, it's going to actually create a current because it's called ionizing radiation. That means it creates ions because it hits things at such high speeds with such high energy. And as it creates ions, and I should say this is a partial vacuum, not a complete vacuum, so there are some ions in there. I'm sorry, it's very early in the morning, I'm very tired. I'm not meaning to say vacuum. There's not a vacuum in there, there's actually a non-reactive gas in there, like argon gas, as you can see by looking at the diagram here. Okay, so you've got something like argon gas. It's non-reactive. It's not going to react with anything. But when ionizing radiation hits it, it will have some electrons stripped off of it. It becomes an ion. And then a current will flow through the Geiger counter. Okay? And as it does, every time that a particle flows through there, you can actually count the radiation that you have. Okay? So that's how a Geiger counter works. Okay, and then the energy in nuclear reactions, tremendous amount of energy stored in nuclei. And I'm going to go through this fairly quickly, but I kind of want to talk about this because it's interesting. Einstein's famous equation equals mc squared relates directly to the calculation of this energy. Okay, and so basically what happens here is in most chemical reactions, if there's any mass converted to energy, it's been very, very, very minimal, okay? But in nuclear reactions, it's a little bit different. In nuclear reactions, you actually have a significant amount of mass being converted into energy. And I say significant, significant compared to any other chemical reaction. It's still not very much, but just even the conversion of a small amount of energy amount of matter can create a huge amount of energy, okay? So the mass change for the decay of 1 mole of uranium-238 is negative 0.0046 grams. Okay, so we have the equation E equals delta M C squared. Okay, so we can actually figure out the change in energy if we know the mass change. Okay, now the mass is decreasing here. We're losing some mass, which means that we must be gaining some energy. Okay. So the amount of mass that we lose when 1 mole of uranium-238 decays is 0.0046 grams. That's a fairly small amount, okay? But if we plug that into this equation, delta E equals, and I'm just going to use a positive here because this is the amount of mass being lost, 0.0046 grams times the speed of light squared, which is 3.00 meters per second squared. And this whole quantity is squared, okay? I'm sorry, not 3.0. Again, I'm very tired. 3.0 times 10 to the 8th meters per second. And then square the whole thing. There we go. Okay, so when we multiply these two together, obviously you're going to get a huge energy change here, right? This is going to be very, very large. So the amount of energy you end up getting out when you lose 0.0046 grams of mass is 4.14 times 10 to the 14th, and I believe the units we end up with here are joules, okay? And that is a very significant amount of energy. Okay, and so 1 mole of uranium-238 obviously gives off a lot of energy, and that's the idea behind atomic bombs. That's the idea behind nuclear fission and nuclear power plants, that sort of thing. There's a very large amount of energy given off, and the reason for that is because in the process, some mass is actually converted into energy. Okay, and so just a very interesting concept that you have. We always think of matter and energy as two different entities, but actually they're interchangeable. One can be converted to the other, and when mass is converted into energy, there's just a huge amount of energy stored in a very small amount of mass. Okay, so that's what Einstein realized, and that was very revolutionary. And I just showed you all that. Okay, now this is another example problem here. And we're not going to go over this one, okay, because I think this video has gone on long enough. The main thing that I want you to know is how to do the half-life calculations. I've never seen one where they've made you calculate the amount of energy from a lost amount of mass. But if you do have to calculate it, just remember Einstein's E equals mc squared, and you should be fine, okay? And then next time we'll talk about fission and fusion, which is very interesting stuff as well. Okay, that's it for today.